Hi, I'm Brett. I'm with Random Guys. We're a virtual band. We do 70s and 80s covers virtually. Some pretty good music. Check us out on Facebook, Random Guys Virtual Band. I play saxophone for the band, but I also do the audio and the video engineering. And I put together a series of videos on audio topics. So if you're doing audio, maybe you're doing house of worship, maybe you're doing live sound reinforcement, maybe you're doing studio recording, or you might just be at home doing your own mixing. If you're doing audio, you might find these videos helpful. So let's check out today's video. Alright, so let's take a look at analog to digital conversion. And first let me describe the setup. This device right here is an oscilloscope. Back before the days of digitization and Pro Tools or your favorite DAW, this is how we used to look at analog signals. This is a tool used to help troubleshoot building amplifiers or fixing them or other circuits. We're actually looking at about a 1 kilohertz, 1000 hertz sine wave. It's being generated by this little device right here. All this is a simple sine wave generator. The knob changes the frequency. You can see as I change the knob, the waveforms move closer together or further apart. Closer together means higher in frequency, further apart means lower in frequency. The scale on the oscilloscope right now is set to, using this knob, 1 millisecond per division. So when you get points of even phase, peak to peak, on one division, you are 1 millisecond from one peak to the next peak, which means you are at 1000 cycles per second, 1000 hertz. So that's a 1 kilohertz analog sine wave we're looking at. Now you can watch what it's doing. It's going, if you look at any point in time, you trace this curve, it moves up, it moves down, it moves up, it moves down. That's what a sine wave does. So what is this we're actually looking at? This is actually a voltage. It's being generated by this signal generator box, being fed through this wire directly to the oscilloscope probe coming in on channel 2. That's what we're looking at right now on channel 2. So we are actually fabricating, synthesizing an analog sine wave from this device right here. And it's being done with a 9-volt battery that's in here. This is an XR2206 function generator chip that I've got set up to generate a sine wave. I use it for injecting a signal in a signal path somewhere just to test downstream from that signal path to make sure things are working. Here, it's just to demonstrate what a signal's actually doing. When you've converted sound into a signal of some sort, that signal is electrical. And you're actually looking at a voltage that is moving up and down. It's getting lower in voltage, higher in voltage, lower in voltage, higher in voltage. And what we're going to do is sample this voltage at very finite periods of time, and wherever that sample is, that's going to be a digital representation of that waveform. So we're going to take snapshots basically, and we're going to convert that snapshot into a digital byte in this case. I'll show that in a second. And so this is, as I mentioned, a waveform. Usually a waveform is not a pure sine wave like this. It's made up of a bunch of sine waves, and therefore it turns into a complex waveform. Any kind of sound that happens in real life is almost never a pure sine wave like that. It's comprised of a bunch of sine waves at various frequencies and at various amplitudes, all happening simultaneously. All right, so let's take a look at what happens when we actually convert this to A to D. So I'm going to turn this off. Just remember the voltage goes up and down, and it does it very fast. At this point it was going up and down at every 1/1000th of a second. And so we're going to do this very slowly so we can watch this happen in real time. So I'm going to go ahead and take this probe off of the oscilloscope. We're not going to be using channel 2. We're going to switch over to channel 1. This wants to come off. Simplify what we've got going on here. Just get this out of the way. You'll now switch to channel 2, or channel 1. We are now on channel 1, and we're going to be looking at DC voltage. Let's see what we've got set up here. This is a power supply. It converts 110 volts standard house power into plus volts on this terminal, ground, plus 5 volts on this terminal. So plus 12 volts, plus 5 volts ground is common to both. We're powering this circuit right here. If you can see this circuit, we're powering this circuit with plus 12 volts. This is a circuit that does analog to digital conversion. The main chip on this circuit is an ADC0804. It's an 8-bit A to D converter. It takes a voltage in and converts it into 8 individual bits or 1 byte of binary information. If you recall from our video on binary, or earlier in the video on binary, 8 bits, 1 byte, can represent up to 256 different levels of voltage. So we can sample this input signal and cut it into steps of 256 different levels within the 5 volts that we're going to be putting into this. We're going to be sending in a signal that's 5 volts DC. We've got a potentiometer here, which is a variable resistor. It's 3 pins. The outer 2 pins are sitting across 5 volts. So we've got 5 volts of potential across the outer 2 pins of the potentiometer. The center pin, which is where the voltage that we're reading is going to come from, is going directly to the input to the analog to the digital converter chip. So we are feeding in a DC voltage to this chip for right now for demonstration purposes. It's also being watched by this probe here, and it's also being watched by the input channel to the A to D converter. This little board right here is nothing more than a display board. It's actually letting us see visually the bits that are being output by this A to D converter. This A to D converter chip is being driven by a clock that's on this board. It's a 555 timer generating a clock that tells this when to take a sample. And it's taking samples, I think right now, about 5,000 samples a second, which is slow by today's standards. You wouldn't be able to digitize audio at that rate, but for our purposes, it's more than fast enough. And we will actually see binary. If you recall from binary, over here would be your most significant digit. That represents 128. This is your least significant digit. That's 0 or 1. And you can watch it count up. 0, 1, 10, 11, 100. So you can watch it count up as we go from 0 volts up to 5 volts. So let's go ahead and do that. Also, we watch this trace. This oscilloscope is set to 2 volts per gradient, and so as we move up, that'll be 2 volts, that'll be 4 volts, and halfway would be 5 volts. That's the maximum voltage that we've got set up for this particular demonstration. So right now you can see there's 0. I'm at 0 volts. As I begin to turn the potentiometer, I will start to raise in voltage, and as I raise in voltage, watch it count. There's 1, there's 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0. You can watch it count up as it individually converts this voltage as this voltage rises. Now watch it go on the oscilloscope as I turn. The voltage is going up. Imagine this is happening like at 1,000 times a second. This is going very fast. I'm going very slow here just to demonstrate what it looks like when it takes a sample of a given voltage at a given time. This is constantly taking samples, so I'm just feeding it a steady voltage so we can see what the samples look like in slow time, slow motion. But you can see it count up. Continue, continue, continue. As I raise the voltage, I get nearer and nearer 5 volts. I'm coming up on 4 volts now. There I am at 4 volts. I'm continuing on. I'm coming up to 5 volts. And suddenly, boom, all ones. That is a full binary byte. That's all ones. You can see where I am voltage-wise, right around 5 volts. What would happen if I fed more than 5 volts into this A to D circuit? Well, it can't go any higher. That's as high as it's going to go. So every volt that I add, or 1/10 of a volt or whatever, if I go any higher in voltage for the input, that's all I'm going to get for the output. If you use Pro Tools, used any kind of DAW, if you see those level meters go red, that's what's happening. This is 0 dB full scale right here. I am at full scale. I cannot encode any more voltage after this. If I give more voltage in, I'm going to get a flat line out. That's clipping. That adds distortion to your signal. So this is what 0 dB full scale looks like. I can't go any higher in voltage because that's as high as this thing can go. Indeed, I have more voltage to give it, but I can't encode that voltage. So there's a little bit of voltage additional that I just added that cannot be encoded by this because I'm at full scale right now. So if you watch this go up and down, you can watch it digitize and change the output. This output would be sent to the computer, and the computer would store this as a digital byte. as a representation of the voltage that it was seeing in the signal level at that particular instant in time when the sample was taken. Now, if you've done recording, you know you've got choices at bit depth, and we'll go into that a little bit more detail later. But the bit depth, what does that mean? 16-bit bit depth, 24-bit bit depth. What does that mean? Well, you know that 8 bits, this is 8-bit bit depth right here. I am encoding to 8 bits worth of depth. That means I have 256 evenly spaced intervals of voltage that I can represent this incoming signal. This signal can have any number. It's analog. It's continuous. It can have any number of voltages that can be given to you, but when it presents me a particular voltage, I have to fit it within one of the 256 steps I've got available to me. That's the voltage I'm going to represent it by, and there'll be some error. I won't be exactly at the voltage every time because I only have 256 levels of representation. As soon as I go to 16 bits, suddenly I've got 65,536 different levels within the same voltage range. I can get much finer in detail. And 24 bits gives me way more than that, over 16 million individual steps. So as I get increase in my bit depth, I get much more capable of representing the incoming signal as it really was in real life. I'm not approximating it with a bunch of error due to the limited bit depth that I've got. So this is an 8-bit A to D converter. Its bit depth is 8. Most of the industry today will support up to 24 bits of bit depth, so 24-bit A to D converters. This is a simple A to D converter to kind of drive home this concept of bit depth and what it actually looks like when you take a voltage, an analog voltage, and feed it to an A to D converter chip, which is happening right here, and the information that it's actually sending to the computer as a way of representing that particular signal at the instant in time that sample was taken. So I hope this demonstration helps, and we'll move on.